Welcome back to ChemDoctor, and this video is going to be the 6th video in the playlist that deals with weak acids and weak bases. And specifically what we're going to do is we're going to dissect the classic strong base weak acid titration and produce the classic pH curve. So that the aim of this is for the viewer to come out of this series of videos, which I think is going to amount to 2 of them, for the viewer to be able to describe and understand the various aspects of the pH curve that comes from the standard strong base weak acid titration. Now, I think it's important to mention that the viewer is going to need a few things in their background to fully get the maximum reward from this presentation and the one that follows it. First and foremost, you should be comfortable with doing weak acid calculations and weak base calculations using Kas and Kbs. Secondly, it's important for you to understand the basic definition of a neutralization reaction and be familiar with a general titration where we have some kind of base or acid in a burette. We have some kind of opposite sample in the collection flask, and we are going to titrate the acids. In this case, we're going to have 0.1 molar NaOH in the burette. We're going to have our weak acid solution in the collection flask, and we are going to titrate to an endpoint using an indicator called phenolphthalein. Phenolphthalein is clear in acidic conditions, and at the end point where we're going to shut down the stopcock and turn off the experiment, the pH is going to be about 8.8 and the coloration of the solution will be light pink. Now, I assume, and this is important, and if any of the things that I've mentioned are not true, then the viewer needs to go back and acquire that knowledge. Otherwise, you're not going to get out of this couple of presentations what you really need to get from this. And one of those issues is the difference between endpoint and equivalence point. All right. So the equivalence point of this reaction is where we have reacted utterly all of the weak acid that we've put into the reaction. And you'll notice that we're starting in the collection flask here with 20 mils of 0.1 molar acetic acid. If we calculate the moles of this, all right, by taking the volume, changing it to liters, so it'd be 0.02 liters times the molarity of the acetic acid, the acetic acid solution, then the maximum amount of acid that we have available to react with the sodium hydroxide, is 0.02 moles. 0.02 moles. All right, and the equivalence point, therefore, will be the point where all 0.002 moles of the acid has been used up. So it'll be the point where we have added the last little bit. We drip in a fraction of a drop of NaOH, and the last of the acetic acid, the last of the 0.002 moles, is converted into the acetate ion. So at that point, at the equivalence point, we are literally going to have 0.002 moles of sodium acetate in solution. So coming back to the general idea of the titration, we're reacting a strong base with a weak acid. The other crucial thing for the viewer to understand is that the base hydroxide is a very, very strong base by comparison to the acetate ion. So there's going to be 2 things going on all the way through this process. The first is, once we add sodium hydroxide to this, we have a stoichiometric reaction. In other words, the reaction between the hydroxide and the acid goes to 100%. It's not an equilibrium reaction. But once the hydroxide is reacted with the acid, now we're in a situation where we have an equilibrium reaction. So there's going to be basically 2 calculations we have to do for each of the transitions here that will allow us to plot the pH curve of this titration. All right, now what I'm going to do in the first video is we're going to calculate 3 points on this graph. We're first going to calculate the pH of the solution where no hydroxide ion is added. All right, so literally what we're doing here is we've got our 20 mils of acetic acid, the 0.1 molar solution of acetic acid in the collection flask, and we're going to calculate the pH of that solution. So we have, and I'm going to work in the shorthand notation here. We have our HA, which is going to be in equilibrium with H3O plus A minus. All right, our Ka is shown up here on the right side of our screen. It's 1.8 times 10 to the minus fifth. So our ICE, or the box as I call it, is going to look like this. The initial concentrations of the H3O plus and A minus are 0. At equilibrium, we're going to have a shift to the right. So this will be minus X, this will be X, and this will be X. So our equilibrium expression will be X squared, and we're going to neglect the X out of the box. If you run the percent dissociation, which is equal to the 5% rule, you will see that this neglection is fine, and in the interest of efficiency, I'm not going to do it here. So my X value, which is equal to the concentration of H3O plus, is going to equal 0.00134 molar. All right, and when we take the pH of this value, which is minus the log of this value, the pH of the solution before any NaOH is added, before any hydroxide is added, is going to be 2.87. So coming up here, what I'm going to do is go ahead and mark that point on our graph. This is and this is going to be, you know, approximate stuff here. So I'll put a red dot there. That's where we're starting with the titration. All right, before we have added any hydroxide to this mixture. Now, the next point that we're going to acquire on this graph is going to be the place where we literally have used up half of the acid. So that means we're going to drip in enough sodium hydroxide to do away with 0.002 moles of the acetic acid. So that means we're going to need 10 milliliters of the 0.1 molar solution. That's going to give us, if you run your calculation, an introduction of 0.001 moles of the hydroxide into the collection flask. So that's going to reduce our acid to 0.001 moles. All right. Now, here's the thing that the student needs to recognize about this. We've lost 0.001 moles of the acid. We've produced 0.001 moles of the conjugate base of the weak acid. So we have a new kind of equilibrium problem here. Whoops. It's my dyslexia coming in. All right. We've changed the problem now. We've added 10 milliliters of the 0.1 molar hydroxide solution, which I'll write like this. So now, writing the equilibrium reaction, we have HA is going to H3O plus A minus. Now, we need concentration in here. So coming back up to the moles that we've established for the conjugate base and the conjugate acid, we need to divide by the new total volume. So we've added 10 mils of the base. We had 20 mils of the hydroxide to start with. So we're going to be dividing now by 0.03 liters, or 30 mLs, converted to liters. So 0.03 liters. So our new concentration at this point is going to be 0.0333 molar of the acid and 0.0, sorry. So it's going to be 0.0333 molar of the base. All right, so we have literally the same amount in concentration at this point, and this is a significant issue that I'll get into in a minute. So initially we have 0.0333 0.0333 molar of the weak acid, and we have 0.0333 molar of the conjugate base. Setting up our equilibrium expression, we're going to have x times 0.0333 in the numerator divided by 0.0333 in the denominator, and this is equal to the equilibrium constant, which is 1.8 times 10 to the minus fifth. So our x value here is equal to the H3O plus, which happens to equal directly the value for the equilibrium constant, or the Ka. So my pH at this value is minus the log of the Ka, which is equal to 4.74. Or another way of looking at this, once we have used enough hydroxide to eliminate 1/2 the concentration of our weak acid, then pH is equal to pKa for that weak acid. Now if I put this spot in here, this is about 4.5 on our pH scale. We've added, I'll run some dots up here. We put in 10 mils of the base, so let's just establish this going up like that. Roughly, my artwork is not the best. We have about 4.5 here, so we're going to go to about 4.75. So my next point on this graph is going to be right about here. Well, I'll put it in red. All right, now we need to keep moving right now, and I'll come back and talk about the significance of this later. The main thing is to recognize is that at the halfway point where we've used half of the weak acid, we've titrated half of it away, you're at a unique point on this graph where the pH is equal to the pKa, because we took minus the log of the actual Ka value. All right, so at this point on this graph, we can actually find the equilibrium constant of any weak acid that we might be titrating, say it was an unknown. Now, what we're going to do next is calculate the pH at the equivalence point. So we're going to add 20 mLs of sodium hydroxide of 0.1 molar NaOH. All right, OH minus. Now, that means at that point where we have 20 mLs of the 0.1 molar, that we have added 0.002 moles of hydroxide, and that means that the HA has gone to 0. All right, and the conjugate base now, the acetate, is 0.002 moles. All right, now we're going to need to find the molarities. Let's go ahead and do that right now. So we've added 20 mils of hydroxide. The original solution had 20 in it. So we're going to divide by 0.04 liters at this point. And the A minus concentration is going to equal 0.05 molar. All right, now bringing that down, we have a different equilibrium at the equivalence point of this titration. So at the point where we have added enough hydroxide to eliminate the HA, we now have produced 100% A minus. It is the major species that we have in solution. So to find the pH now, we have the equilibrium problem of a weak base added to water. So this is the same difference as adding the salt of a weak acid to water, and then we have to find the pH. So what we're going to find first is we're going to find the pOH, and we're going to need the Kb for this. So we have 0.05 molar of A minus, 0 of this and 0 of that. Then we're going to have 0.05 minus X, then X and X. So X squared over 0.05 is equal to, all right, now we need the Kb, so it's going to be 5.56 times 10 to the minus 10th. So running the math, the X value here, which is my hydroxide, solution, fix this up just a little bit quickly. All right, is going to equal 5.27 times 10 to the minus 6 molar. So the pOH for the solution, taking minus the log of that value, is going to be about 5.28. The pH, which is what we need, and I got this by taking 14 and subtracting 5.28, is going to be equal to 8.72. All right, so coming back up to our graph then, the pH of the equivalence point is going to be somewhere along this line, right? Let me just put some dots out across here. All right, and then we utilize 20 mLs of the sodium hydroxide solution. All right, so I'm going to change the color here. So in essence, this spot right there is our equivalence. All right, so what I've done on the graph to close this video, all right, is we've established 3 points during the standard strong base weak acid titration. The first point is the pH of the solution before any hydroxide is added. The second point is where we've added enough hydroxide so that the concentration of HA exactly equals the concentration of A-. This point that is marked in blue, this is the point where the titration essentially is ended because we have reached the equivalence point. That is the point where we've added enough hydroxide to eliminate all the weak acid that was in the reaction flask, producing 100% A- at that point. The A- establishes the pH of the equivalence point. You'll notice that the indicator we're using has an endpoint whose pH is about 8.8, and the equivalence point, the place where we've used up all the weak acid, has a pH dependent on the conjugate base that happens to be 8.72, which is very close to the endpoint of our indicator, phenolphthalein, which is a requirement for a laboratory like this. Okay, and with that, I'm going to close this video, and we'll pick up part 2 in the next sequence.